I've always liked being around labs, and I kind of grew up around them. My father is a professor too, and he's an experimentalist, and so he's worked with lasers and in spectroscopy before, and so I've always been around lights and lasers and colors and strange experiments that went on in the middle of the night. So I started off working with femtosecond lasers, and they looked like very, very nice toys that I could not play with, and so I always thought that they were a set of magical games that I could get to eventually. I'm Fiorenzo Omenetto, Fio Omenetto. I'm a professor at Tufts University in Boston, Medford, Somerville. So I did a lot of my nonlinear optics and work at Los Alamos National Lab, and then I accepted an academic position at Tufts University, and I moved from a physics department to a biomedical engineering department, which is unusual, at least for me, because I'm not a biomedical engineer. Down the hall from me, there's the office of David Kaplan, who is the head of the biomedical engineering department, and has been working on silk for the past probably 20 years or so, and mostly used silk as a material for tissue engineering. And so we started talking about doing things together, and nothing really materialized until he showed me what was supposed to be a corneal implant, so a film of silk that was very transparent and looked nothing like the silk that I was used to seeing. And so we started talking, and I suggested that we could do maybe some optics out of it, and then we started transforming silk into something that now looks like this. So this is a pure film of silk fibroin with a lot of optical components inside of it, and so that's part of the transformation that we're doing today. So we're going from this to this with easy steps. Once you get past the first reaction of seeing silk in a different form, is why would you even bother? So there are some arguments from a material processing side, and these have been addressed a lot by David in trying to actually get silk inside of the body, so as tissue engineering implants. But I think that the attributes are that you have green chemistry, so all the purification process has no toxic byproducts, and it's all water-based, and it's all done at neutral pH. And so it's a very benign process, and that in and of itself is something that is of some difference compared to conventional biopolymers or conventional polymers. The additional things are that silk this purified silk is implantable. It's edible if you so wish, and if you're really hungry, I guess. But it also has a particular property, which is during the formation of the film, if biochemical components are mixed into the precursor, so are mixed into the solution of the pure silk fibroin in water, as the film hardens, then these biochemical components are entrapped in the film, and their biochemical activity is maintained, which then enables to do active optics in a way that really is very hard to do otherwise. The ultimate dream would be to actually include some of the components that we know that can be maintained active, like for example antibodies, and then have antibodies perturb the structure so that you can detect, for example, I don't know, E. coli, for instance. And so you can tell if one of the things that we've talked about earlier was whether, for example, you could put this in a bag of spinach and actually see whether the spinach is safe to eat or not.